Hello everyone and welcome back to an L582 modeling and control of electric machines and drives. For the last lecture we started talking about the starting of three-phase induction motors, and like we said, what we mean by starting of the three-phase induction motor is reducing the very high current that the motor draws at the starting instant by pressing the start button. Okay, like we said, this high current makes plenty of problems. Mainly, he increases the copper losses inside the machine and reduces the voltage of the bus that the machine is publicly connected to in your grid, and that is not good for the other loads that share the same bus with your motor. Okay, so how to deal with this is basically, like we said, is the starting current equal the voltage divided by the total impedance of the machine. The slip equals 1 at the starting instant. So basically, to reduce the starting current, you want to reduce the voltage of the machine or increase the total impedance of the system. Okay. So we just start talking about the methods we can go with to do this. Like we said, with the first one, with the full voltage control starting, we call it direct online starting. That is, we don't use actually any method to reduce the starting current, just leave it alone. And this is used with small motors because actually whatever the current goes up, it's not that much. So we don't need to go and have a specific method to reduce a current that is already not that high. And that, like we said last time, is the control and the power circuits of the motor, which is power circuits basically a contactor, which is the three-phase switch that can be remotely controlled to just close or open. Okay, and you have two pieces of protection. One of them is a fuse. It's a protection against short circuits, and an overload relay, which is protection against overloading, which a small increase in the current but lasts for a long time, and contrary to the fuse, which is protects against short circuits, which is a very high current and that just lasts for a small period. Okay, and that was the control circuit, which is have basically two push buttons, one for the start and one for the stop. And like we said last time, it's just how you actually can control the motor in terms of just starting and stopping. We don't control anything here, just a start and stop, and have a little bit of protection over the motor just to protect it. Obviously, if you're talking about a big motor, a very one that is basically can be used for a very big applications, you will need more protections, not just those simple protections with the fuse and overload. Well, sometimes you use a circuit breaker instead of the fuse, and you use different protection relays that can just protect against the under voltage or the over voltage, the earth leakage, all that stuff. But that's, like I said, it's just about the protection courses, not here. So we're talking here about the standard protection you just find for a standard motor out there in a regular industrial application. Okay. Like we said, we can just find the starting current of the motor cut draws without any means of reduction for this starting current. That means a starting method or something. Like we said, we can just simply even use the equivalent circuit to find this current, putting the slip at 1 because that's the starting slip. If you have the equivalent circuit parameters, but if you don't, you just have the machine, so the manufacturer providing you what we call the starting code. You can find it on the nameplate of the motor, which is just, you'll find it attached to the outer case of the motor and you can see it. You will find a code over there that you can come to this table to find a range for the expected starting kilovolt ampere per rated horsepower, and then you can calculate the starting current from it, like we did the last lecture. And if you want to reduce the starting current, you're gonna go with one of these methods. The second one we just talked about is adding an impedance to the stator terminals for the starting period, and then add a switch in parallel with it and switch it on after the starting period passes, and this bypass this resistance or impedance and just get the motor directly to be connected to the supply voltage. This impedance take some voltage drop, which is subtracted from the main supply, the voltage from the supply voltage, so the motor voltage is a little bit reduced, and this reduces your starting current. The second method we're doing the same, but adding resistance to the rotor winding if you're talking about a on rotor machine via the slip rings and brushes. And like we said, it's basically increase the total impedance of the machine, and thus reduces your current. Like we said, this is the only method that can increase the starting torque while reducing the starting current, and that's very good. But like we said, it's not that common because actually the on rotor motors are not that common compared with the square cage motors. And we can use auto transformer, which is basically you can just connect the supply to the primary winding and the motor to the secondary winding, and using the variac, and you can just control the amount of voltage that go into the motor for the starting period, and then you gradually increase it to the rated value after the starting period passes. Okay, we talked in detail about every method of this, and like we said, each one has a pros and cons, and you as an engineer get to choose. Okay, but actually none of those methods are that common in the industrial applications. You can see some of them somewhere, but the two very common methods are the two methods we are talking about today. Okay, so go on the same path. I'm gonna say here again, starting of three-phase induction motor. Okay, and that is continued. For the fifth method, we have here what we call using soft starters. What is a soft starter? Okay, the soft starters are basically power electronic converters used to control the voltage. Okay, so rather than just having an auto transformer or other stuff to just control our voltage to reduce it at the beginning, we can actually go with power electronics. Remember we talked about variable speed drives or V over F speed control of three-phase induction motor. So that is our three-phase induction motor, and rather than connecting directly to the supply, we use our power electronics again. So here is an inverter. Okay, and here is your DC link capacitor, and there is another converter which is basically a rectifier, and here is your supply, V supply. Remember we used the same thing before to control the frequency and voltage of the motor. We're here not concerned about controlling the frequency anymore. We just use these power electronic stage here, and that is what we call a soft starter. Okay, not just this, but with the control algorithm that's applied to it. Okay, so what we do with this, we design the control algorithm that generates the driving pulses of the inverter to produce low voltage at starting, and that is which reduces the starting current, I starting, and gradually increase it till its rated value after the starting period passes. Okay, so the same idea we used before with controlling the speed of the motor. Remember when we said we can control the frequency and the voltage output of the inverter, which is basically going to the motor here. But here we don't more concerned about the frequency, we're more concerned about the voltage of the motor. This one can be controlled by controlling the pulses that is going to this inverter. So what we do is we start the motor by a low voltage, and this will reduce your starting current, and gradually control the inverter pulses to increase the voltage applied to the motor until you reach the rated value when you pass the starting period. and that's what can you basically do. Okay, that's why we call it soft starters, because we gradually increasing the voltage. Okay, and you have so much flexibility, so gradually increasing the voltage, and that is why we call it soft starter. Okay, guys, the whole point, yeah, it is much better now. The whole point is you can, or if the motor has already variable speed drives for controlling the speed using V over F method, it can also be used for soft starting. Okay, because it's just the same power electronic circuit used for variable speed drives. The whole point, it has different control algorithm. For the variable speed drives, we just have a control that is mainly, or the control scheme just heading for the V over F speed control algorithm, if you remember. But now we don't care about that. We just need to gradually increase the voltage from a very small value up to the rated value. But still, it's the same power electronic circuit that can be used. It is just you need to have another control scheme that is control the same power electronic circuit. So I can actually use the same circuit to do the same thing, which is very good if your motor already have a variable speed drive for V over F speed control. Okay, so again, what about the pros and cons? Okay, so the pros for this thing, I'm gonna say less maintenance requirements compared to auto transformer. Okay, remember the auto transformer? The auto transformer is basically a machine that requires almost much higher maintenance compared to power electronics compact devices. Okay, the most important pro here, the most important advantage of this one is flexibility. That's why we call it soft. Okay, the whole point is you have a full control, almost full control over how much you want to reduce the voltage compared to other methods. Okay, like adding resistance to the winding of the stator or of the rotor, where you don't have that much flexibility. You have just different steps you can use for these resistances, but it's not that soft actually. For the auto transformer, it's a little bit soft, but again, it's not that much flexibility because you are also governed by the turns ratio that is just provided for you from your auto transformer. But using this, you can almost have so much more flexibility for choosing how much reduction in the voltage you want, and also what is your rate of increasing for the voltage back from this reduced value to the rated value after the starting period pass. Okay, guys. And the other thing is that is more compact size. Okay, so if you're gonna see a real soft starter, is not that big. It's a small box you can use just for controlling the motor like that, compared to have big resistance to add it to the stator or the rotor, or have an auto transformer where it's a totally separate machine you use or something. So yeah, if you're the size you're concerned with, so that's a good method to go with. Okay, but what about the cons? What's your problems here? Okay, so relatively high price. Okay, by the way, it's the same problem even with variable speed drives with V over F speed control. While it's a very good method, but this power electronics controlled stuff is basically pricey. It's expensive. It's not that cheap to do with actually. Okay, and that's a disadvantage for all that you can use power electronic switches to drive a motor. It's basically expensive. Okay, and yet we are doing the same by reducing the voltage. So reducing voltage resulting in reducing the starting torque. Again, like we said, it's almost inevitable for any method, except for again adding resistance to the rotor winding, but still a disadvantage to mention. Okay. Okay. So that's the guy we start talking about here, what we call the soft starter, by using power electronic switches to do your job. Again, like I said, it's very convenient if you already have your motor have a variable speed drive for V over F speed control, so you can use the same circuit for different purpose, which is so much will save you a lot of money. I'm saying, apart from having two different devices, one for control and one for starting, so you're using almost the same device to do the two jobs, and that's very good. But if your motor does not have a variable speed drive like that, and you don't need a speed control for the motor, so the soft starter should be very expensive option to go with. Okay, that's why we can go with the other option, which is the last method I'm going to talk about here, and actually it is the most commonly used one, which is the Y delta starter. Okay, and yeah, it's actually the most common one. Okay, what is this and how we deal with it? So what I mean by Y delta starter is basically this idea that we start the motor as Y connected, and after the starting period passes, we switch it to delta connected. That's what we mean by Y delta starter. Okay, so you start the motor as Y connected, and then you switch this connection to be delta connected. Okay, first how we can do it, and after this I'm going to discuss with you how this actually can act as a starter and reduce the starting current. Okay, so how you do this is basically using a very common circuit for the Y delta starter. I'm gonna grab you a photo for it down here. Fine. So like you can see it here, that is the Y delta starter. Okay, so let's just have a look at it. Here is basically your three-phase supply point. So the voltage comes here from the supply, and here is our motor. Okay, that is our three-phase induction motor. Those are the terminals of the machine. So that is phase A terminals, call it U1 and U2, and here is phase 2 terminal. I'm gonna get blue, so that is phase 2 terminals. That's 2 terminal for the phase, and that is the last one, phase C terminals, call it W1 and W2. Okay, so the motor has 3 phases for the stator, and that's what we deal with, and each phase has 2 terminals, 2 points, like you know. Okay, so basically our motor most of the time is internally connected to be a Y or a delta, and you just have 3 terminals outside if it is a delta, or 4 terminals if it is a Y connected, because you know the Y connection has a neutral point. But for this method to do, we need to have all the 6 points of the winding out. So our stator winding cannot be internally connected as Y and delta, and you just have 3 points out. We need all the terminals out because we're gonna change the connection with time. Okay, so for this you have the main contactor of the machine. Remember the contactors when you talked about the direct on line? The contactor is just basically a 3-phase switch that can just close or open, and that can be remotely controlled, so you can just switch it on or off from your control room, actually in your industrial facility. So that's the main contactor that's connected to the motor, like the circuit we just investigated for the direct online method. But here we need 2 other contactors. Okay, that's a contactor, and he called it the delta contactor, and another one we call the star contactor. So the delta contactor, from its name, you just basically, if you close it while you're closing also the main contactor, the motor will be connected as delta. If you just open this delta contactor and closed the start contactor, the star contactor or the Y contactor, because you know it's a star or Y, whatever you want to call it. So yeah, the star or Y contactor. You're basically connecting the motor as Y. It's simple as that. You can just go around this if you want to look at it here. So bear with me. For the delta conductor, like you seen here, for this delta contactor, look what this contactor, if this closes, what will happen. It's taken from here, that is phase A, if you remember, of the motor. That's taken from phase A, going here like that, down like that, back here, connected it to the second one, which is phase B. Okay? And the second one is taken from here, that is phase B of the motor. And thus, if you just follow it down here, you're gonna connect it here to phase C. And back here, from the motor again, that is phase C of the motor. If you just follow it with here, going down here, down there, it's connecting it to the end of the first phase. It's how you connect as delta, if you remember. You're just connecting the ending of one phase to the beginning of the next phase. That's how you can connect as delta. Okay? That means from your lock in here, if you closed the main contactor and the delta contactor, you're connecting this motor as delta. But what about the Y? Okay? Like you see in here, that is the Y contactor, and how it is doing this is you basically seeing that is the three phases of the motor connecting here. And if you close these switches, those are all closed, you are basically having a short circuit down here that's connecting those together. And that's how we do to connect this as a Y contactor, is we having the three terminals of the motor connected together in one point, while the other three terminals is your line connection that can use for connecting it to the supply. So if you want to connect this motor as Y connected, you basically close or switch off this Y contactor and the main contactor at the same time. Okay, guys? So that is basically how you can go with the connections for this machine. Okay? That is how we can switch from Y connection to delta connection, or from delta connection to Y connection if we want to do. And that's by the way, it's the overload relay, the same like we talked before in our DOL. Okay, guys? So that's basically how you can do this switching from Y connection to delta connection using just those contactors. Okay, so our procedure here. Okay, so number one, you close, or let me say switch off, switch on the main contactor and the Y contactor together to connect the motor as Y. Okay? Number two, set a delay timer for a period equivalent to the starting period of the motor. Okay, how you know this period of the starting? That is mostly by experience of the operators. Okay, and after this passes, you switch off the Y contactor and switch on the delta contactor, and just while the main contactor is still on, to connect the motor as delta and keep it like that. So that means is the regular connection of the motor is the delta. So the motor will be connected like delta regularly and all the time. But just at starting, we will be connecting it as y. Okay. But again, okay, that's good. That's how we can just do this. But how this actually can reduce our starting current, that's the whole point we need to look at. Okay, it's how actually this can be reflecting and how we can actually reduce the starting current. It's the whole purpose of all that. And that's how what I'm gonna do now. Let's investigate all happen here. So like we said, the regular connection is the delta connection. That is the regular connection of the motor. Okay, so the motor is just will be continuously be connecting as delta, will be just a y connection just at the starting period. So let's look at the motor. It is just connected like delta. So here is your winding if they connected like delta. Okay, and this is the connection for the line to line, and here is your line current, which is basically the current we want to reduce. If you remember, like I said, we mostly want to reduce the current that's coming from the supply, so most of the time we're looking at the line current. Okay, we didn't care about if it is the motor is y connected because the line current equals the phase current, but here for a delta connection they are different. Okay, so that is your phase current. I'm gonna call it I phase delta just for discrimination, and that is I line delta. Okay guys, or okay, and you know this voltage here over the phase is V phase in terms of delta, and still that is line to line in terms of delta. Okay guys, and let's do our calculations here. So I'm gonna ask you here, find me the phase current please. So I phase here in terms of delta connection, like anything, will equal V phase in terms of delta connection over Z phase, the impedance of the phase. And the impedance of the phase, it doesn't matter if it is Y connected or delta connected because it is the same winding, so it doesn't matter, yeah? And this will equal V line to line delta over Z phase. Why? Because you know for delta connection the V line to line equals V phase. You know that. Okay guys? What about I line? Because that is what we're more concerned about. I line delta for the delta connection equals square root of 3 times I phase. That is for the delta connection how it works. Okay? So just substitute over this, so it is square root of 3 I phase from top here, it is V line to line over Z phase. Okay guys, so keep that in mind. I line for the delta connection equals square root of 3 times V line to line over Z phase. What about Y connection, which is the starting connection? The delta connection, I'm gonna call it for you running connection. Okay, that is the connection, or the motor will keep running with it, but the Y is just the starting connection. Okay, if the motor is started like Y connection, the phases will look like that. You have 3 phases like that and connected like that. Okay, again, that is your line connections, and that's what we're more concerned about. That is our I line, which is more concerned here. I'm going to call it I line Y, and that is V line to line for the Y, or for the delta actually, it's still the same line to line. That is V phase here, that is the voltage over the phase for the Y connection, and that is the current going inside the phase for the Y connection. I'm going to do the same thing here. So if you want to calculate I phase for the Y connection, it is still equal V phase for the Y connection over Z phase. For a Y connection, the V phase equals V line to line divided by square root of 3. That is for Y connection, V line to line equal square root of 3 times V phase. That's why V phase equals V line to line over square root of 3. That is divided by Z phase. Okay guys? And if you want to find the line current for it, for the Y connection, it directly equals the phase current, because that is Y connection. The line current directly equals the phase current, and that is V line to line over square root of 3 Z phase, like we just said. What I'm going to ask you to do here is please give me the ratio between I line in terms of Y connection over I line for delta connection. I line for Y connection is just, we found it here, V line to line divided by square root of 3 Z phase. And divide this by the I line for the delta connection, we found it just here. I line for delta connection is square root of 3 V line to line over Z phase, so I'm gonna just divide by it, so that here square root of 3 V line to line divided by Z phase, so that goes up in the numerator. Okay? So V line to line goes V line to line, Z phase goes by Z phase, and you have here square root of 3 multiplied by square root of 3, and this gives you 3, so that is 1 over 3. What does it mean? Does it mean I line in terms of Y connection equals 1/3 of I line in terms of delta connection? Understand what I'm talking about here, guys? We said that the Y connection is the starting connection, while the delta connection is the running connection, yeah? We connect the machine as Y for the starting, and after just past the starting, we go to delta. And that means using the Y delta starter here, I starting as 1/3 of I running. So using this method, you can reduce the starting current by an order of 3. And that is pretty much sufficient for most of your applications. Okay, guys? And that's why that is the most commonly used method, actually. Why? Because again, if we're gonna talk about the pros and cons of this kind, you'll just see what I'm saying about here. Okay? So the pros of this method are number one, it is very simple method. You just need to switch the connection from Y to delta. Okay? The other thing is it is much less expensive, as you just need 2 more contactors, okay, which are more or less switches, okay, compared to other equipment like using auto transformer or impedances or power electronics switches for the soft starters and all that stuff. They are just mostly expensive compared to these 2 contactors you can just use. Okay, so that's why it's so much attractive for these applications. Okay, guys, but still you have cons to deal with here. Okay, first thing, it not flexible. Okay, you just have fixed reduction ratio, which is 1/3. You cannot have any control of how much you reduce the starting current. It is just 1/3. You just reduce it by 1/3, which is a lot actually, but if you want to go lower than this or higher than this, you cannot go with this method. Okay, it's not flexible. The other thing, the running connection has to be delta, you know. For this method to work, that has to be like that. The motor will be starting or just working as delta all the time, but at the starting we connect it as Y. If you want your motor to work as Y connected after this, it will not work. Okay, so that means you are forced that your motor will be connected as delta. If you want to connect as Y for any reason, you will not be able to do it. Okay, And the same idea, reducing starting torque, because again it is doing the same thing. If you want to reduce the voltage, reduce the current, you're basically reducing the starting torque with it. Again, it's inevitable, but again it's a disadvantage to deal with. Okay, but still, with all of these cons, it is the most attractive method, because like we said, we like to go simple and less expensive as much as we can, and this method by far very simple and very much less expensive compared to other methods, and that's why it is the most commonly used method you're gonna say there for starting the three-phase induction motor. Okay, guys? Okay. That is the end about my talking about the starting three-phase induction motors. So, talking about three-phase machines, three-phase induction machines, actually we started talking about like any other kind of machine, started talking about the construction of the machine, talked about the theory of operation of it, talking about the modeling, which how we find the equivalent circuit model of it, used it to expect the performance of the machine, and tested the machine in the lab to determine those equivalent circuit parameters. And we dealt with how to control the speed of the machine, which is a very important topic, and gone to the starting of it, how to reduce its starting current, like we said. Okay, before I leave three-phase induction motors, I want to just have some time to talk to you about the other modes of operation that the machine can work at. Yeah, like I said, we're more concerned about the motor operation for the machine, because three-phase induction motors are the workhorse of industry, and that's how the machine mostly dealt with. But actually the machine can work also as a generator, okay? And that's just have a look quickly about the modes of operations of three-phase induction machines. Okay, I'm gonna not saying motors here, because now we're gonna talk about other stuff but just motor, you know. So actually the first one is the motor mode, which we've been talking about all of the time. Yeah, how to distinguish actually a motor mode? You know, it is P electric is your input and P mechanical is your output. It's how any motor works. It takes electric power as input and just convert it into mechanical power. Okay, guys? How the machine works internally like a motor, if you remember, that is a stator, and this stator has rotating magnetic field like poles, okay? And those guys are just rotating around the circumference of the machine by the synchronous speed. And your rotor having the same set of poles. So but you have here south and here north, and you have those connected together or just coupled together like we said before, and rotating together at the same speed. But what about the rotor body itself? It rotates at the same way here. So the mechanical speed, that is how the rotor body goes, and that is how the synchronous speed goes. The synchronous speed is the speed of the magnetic field, and the mechanical speed is the speed of the rotor body itself. Okay. For the motor mode, like we said all the time, the mechanical speed, which I mean by it is the rotor body speed, because you know the rotor field had the same speed as the stator field, but the body is just a little bit behind them, if you remember. That's how we define the slip. So the mechanical speed or rotor body, which is Nm, is at the same direction of synchronous speed, which is the speed of magnetic field, okay, but a little bit behind it, okay. That is how we find our motor all the time. So that means basically if the synchronous speed going that way by this amount, your mechanical speed will go in the same way like that, but a little bit less than it like that. Okay? So the mechanical speed is basically less than the synchronous speed for the motor mode, like we said all the time. So if you want to calculate the slip, which is ns minus nm over ns, this mechanical speed is less than this synchronous speed and in the same direction, and that's why the slip, you'll find it higher than 0, just less than 1, because the numerator here is all the time less than the denominator, which is the synchronous speed, and that's why the slip for the motor operation is all the time between 0 and 1. Okay, it will not be 0 unless the mechanical speed unless be 0 unless this mechanical speed equals the synchronous speed, and it will not happen like we're seeing all the time. And it will not be 1 unless the mechanical speed is 0. So if it is 0, then the machine is not working at all, it's not rotating at all, and that's, you cannot say it is a motor or anything else because it's not rotating anyways. Okay, that is how you can just distinguish a motor operation. And that's important to look at the power flow diagram for the motor mode. Okay, that is how we find before, is you have here P input, which is P electrical input, if you remember, and then I start losing, which is here P copper losses in the stator, and P core both in the stator and the rotor. Here I'm going with the exact equivalent circuit, if you remember. The rest is your air gap power, the power that crosses the air gap from stator to rotor, and then you lose some as copper losses in the rotor. The rest is your converted power, lose some of it as rotational losses or friction windage losses or mechanical losses, whatever you want to call it, they are all the same. And the rest is your P output, which is mechanical power. Okay guys, that is a motor mode, which is all the time we dealt with before, so we should be good with this. What are the other modes that the machine can work at? Second one is the generator mode. The machine can also work as a generator, actually, it's not just a motor. How we do this to work as a generator to generate electricity? So for the generator, input is P mechanical, output is P electrical. How we just generate electricity from an induction motor? Simply apply 3-phase AC voltage to stator, okay, to build magnetic field, and apply external mechanical source to rotate the rotor to a speed higher than synchronous speed, which is the speed of the magnetic field. Like that, the machine will act as a generator. So what will happen is the same idea. If the speed of the magnetic field coming from the stator and the rotor goes this direction by this amount, if you apply an external source to mechanically rotate the rotor to just its outruns the synchronous speed, it's being ahead of it, higher than it, now you're talking about a generator. That only happens if the mechanical speed is gone higher than the synchronous speed. And that's obvious. If you remember, you need to have a mechanical source that is force the rotor to rotate, okay? But for here, because we have to apply 3-phase voltage to the stator to build the magnetic field, because if you remember, to generate electricity, to have a generator, you need to have a movement inside a magnetic field. The movement comes by the mechanical source that rotates the rotor, but the magnetic field comes by applying 3-phase voltage to the stator, okay? So the 3-phase voltage applied to the stator will create a magnetic field that is rotating around the circumference of the machine by the synchronous speed. So for the machine to act as a generator, you have to apply a mechanical source and make the speed so much high to be higher than the synchronous speed, and like that, it will be turning into a generator. If you want to calculate the slip here, which equals ns minus nm over ns, you will find the slip to be less than 0, negative slip, because you know the mechanical speed is higher than the synchronous speed. And that's how you know for the generator mode is that the slip is negative. It's very weird to us because we didn't use to this, but yeah, it's for that you can actually find it if you're dealing with a generator mode. Okay, guys? So if you want to look at the power flow diagram for this, it will be just the other way around. Now your P input is mechanical power, because that's a generator. Like anything, you start losing. Now you're losing rotational losses here as mechanical losses. The rest will be the converted power on the router, and you lose some of it at peak couple router, because you remember this input mechanical power is going to the router now, not the stator. Okay, so this power flow of the motor is basically have been reversed. Okay, so the power flow for the motor goes this direction. Actually, if you do the same thing like this, but you just reverse it, you'll find the generator power flow. Okay, guys? So you have the mechanical power going to the router, you lose some of it at rotational losses, the rest is converted power. You'll lose some of the copper losses over the router before crossing the air gap as air gap power going to the stator. Because for the generator, the power comes from the router to the stator, not like the motor, okay? And you lose on the stator the core losses and the copper losses in the stator, and the rest is your P output, which is basically electrical power here. Okay, guys? So this electrical power is on the stator. We go back to the motor, this electric power input is going to the stator, and this mechanical power is you find it on the router, as you can just imagine. Okay, guys? The whole point is, for the generator mode, which you're not finding that much, but you find it actually with mostly the wind energy applications. So a couple of just a very important stuff to keep in mind for the generator mode for the induction machines, okay, is because the induction machine does not have a separate source for excitation, which I mean build its own magnetic field like synchronous generator. The reactive power needed for building magnetic field comes as a part from the electric power on stator. Remember, like I said, you have to apply three-phase voltage to the stator to build the magnetic field of the machine. But where the active power, the electric power that this machine generating goes to the grid, it also goes through the stator winding. So what does it mean? This means the induction generator gives active power P to the grid while taking reactive power Q from the grid to build its own magnetic field, which is not something good. If you remember, we talked about the synchronous generator before. It has a separate source that goes to the router for a DC voltage to build the magnetic field inside the machine, and that's why this generator builds its own magnetic field, and it has an excess reactive power that can push to the grid actually. For an induction machine, it does not have a separate winding, a separate source that go into the router to build the magnetic field. So it has to get some electricity from the grid to build its own magnetic field, and then it gives back power to the grid. So the induction generator cannot provide the grid with a Q. Actually, it needs Q from the grid. While the synchronous generator is much better in this case because it can give P and Q, because it had its own source of building magnetic field. Okay, guys? So the induction generator, while connected to a grid, will take its Q requirement from the grid to build its own magnetic field. If the induction generator is isolated, what I mean by isolated, not connected to a grid, it's just connected to a load in an isolate mode, not connected to a public grid. A capacitor bank has to be installed at its terminals to provide the machine with the required reactive power to build its magnetic field and start generating. Okay, guys, I hope you understand that. Like we said, the very principles, that is to have a generator which is actually generate electricity. It has to have a source of magnetic field and a mechanical power to have a rotation inside this magnetic field. It's how you can just apply the conditions needed for electricity generation. Okay, if you remember, for a synchronous generator, which is the most common generator type, you have a separate source going to the router that is given DC voltage to build its own magnetic field. So it just can build its own magnetic field and have an excess reactive power to give it to the grid. While for the induction machine, it does not have a separate source to build its own magnetic field. You have just the stator, which is connected to the grid, and this you use to generate electricity and push it to the grid, and also use the same winding of the stator to get reactive power from the grid to build your own magnetic field inside the machine. And that's why the induction machine can just have Q from the grid. It does not have the ability to generate reactive power and give it to the grid, and it's just very basic mode like that. Like we said, if you're not connected to the grid, like you have an isolated load or something, then you don't have any source to get reactive power from. So you have to install capacitors, because capacitors give reactive power. So the capacitors installed on the machine's terminals can give it what the reactive power needed to build its own magnetic field and start generation. Okay, guys? So that's how actually the induction machine works as a generator. So that's the second mode of operation. There is the third mode of operation, which is the plugging mode. I'll be talking about it in the next lecture. Okay? So yeah, thank you so much, guys, for joining me today. I hope you find this lecture informative. Take some time to go through it again, and I'll be happy to have your questions. Thanks so much, and see you next time.